have the last few problems from that last section that we talked about. So this is all review. So you guys probably could have done these on your homework without even seeing this. We reviewed it a little bit at the beginning of the year. Do you guys remember log, the next one? So if you have like 9 to the 8 minus x and 27 to the x minus 3, the easiest thing to do is to get, did we already do this? Yeah, we're here? Yeah. The easiest thing to do is to get 9 and 27 with the same base. So what base can we use? 3. So we're going to change them to 3. So we're going to do 3 squared to the 8 minus x equals 3 cubed to the x minus 3. Okay, so if you can do that, always go that route. It is much easier than taking the log. So we're going to have 3 to the 16 minus 2x equals 3 to the 3x minus 9. So then we can say, okay, well, now we can set our exponents equal to each other. So we're going to have 16 minus 2x equals 3x minus 9. So we get 5x, we get 25, so we get x equals 5. Done. All right, but on the next one we have 4 and we have 5. We cannot get those to be the same base. So if we have an exponent that has a variable in it, we have to do a log somewhere, okay, if we can't get them to be the same base. So we're going to just do natural log of both sides. Okay, and you can do any logarithm of both sides, and you could even switch forms, right? You could rewrite it as log base 4 of 5 equals x minus 1 if you wanted to, and then use the change of base to put that into your calculator. So we're just going to do natural log, and we're going to pull the exponent to the front, and then natural log of 5 and natural log of 4 are both numbers, so we divide them out. So our exact answer would be natural log of 5 divided by natural log of 4 plus 1. Okay, and sometimes that might be the answer that's on the multiple choice. You might have to get it in exact form. You might even write that as log base 4 of 5 plus 1 using the change of base formula in reverse, right? The number that was on the bottom is now your subscript. The number on top is your bigger number. But if it is on the calculator section, you can always write this rounded to 3 decimal places. And that's really the one that I prefer on the test because there's so many different forms for logarithms. I like when you round it to 3 decimals. It's much easier for me to grade. So we get 2.161. All right, so when we have logarithms that are subtracted, we can combine those into one logarithm with division. So we're going to have log base 4 of 100 over x plus 1 equals 1. And then we switch forms. So we do 4 to the 1 equals 100 over x plus 1. And a lot of you guys might be able to solve this right now, just using mental math. So if you think about it, 100 divided by a number gives you 4. That number has to be 25, right? So if your denominator is 25, then what's x? 24. So see how like a lot of you guys will kind of overthink things. You spend a lot of time doing simple computations that you can quickly do in your head, right? All right, it's kind of the same idea for this one. Like you can overcomplicate it, this one, and you can say, okay, 5 to the 6 is equal to x to the 3. And then you can think about what 5 to the 6th is. And some of you guys, you know, might have written that on your quiz, what 5 to the 6th was. And it takes a long, long time to do things like that. Or you could realize, oh, wait, I have logarithms, so I can pull a power to the front and say 3 times log base 5 of x equals 6. So when you divide by 3, we have log base 5 of x equals 2, and we can switch forms. So 5 squared equals x. So we end up getting 25 equals x. But even if you had done it the other way, if you had written 5 to the 6 equals x to the 3, just use your, knowledge of exponents. If you're trying to take the cube root of both sides, raise it to 1/3. Right? So then you have 6 times 1/3, which becomes 2, right? So you still get 5 to the 2 equals x, even if you had done it that way. Does that make sense? All right, so that's kind of a quick review of logarithms. We did a little bit more review of that at the beginning of the year. So now we're going to do section 20, which is derivatives of exponential functions. This is the easiest derivative you're going to learn all year. Aren't you excited? The derivative of e to the x is itself e to the x. Isn't that nice? It's weird. All right, so it says look at the graph of f of x equals e to the x. This is a very special graph. And you try to compute the slope at each of these points. So like this point is the point 0, 1. Right? If I try to find its slope, the slope ends up being 1. All right, this is the point 1, e. If I find its slope is e. So anywhere that I find the slope, it's actually the same as whatever your y value was. Okay, so it's the slope of e to the x is itself e to the x. Okay, but you have to be very, very careful. Don't forget the chain. And this is where it gets a lot of people in trouble with e to the x. Okay, so if I had, y equals e to the 2x, right? When I take the derivative, it starts out the same. It's like, okay, it's e to the 2x. But since it's not just e to the x, it's e to the 2x, I have to multiply by what at the end? 2, right? I have to remember the chain rule. Does that make sense? So like if I had e to the x squared, its derivative is going to be itself, e to the x squared, times 2x, right? You have to remember the chain. So the derivative of e to the u is always e to the u times the derivative of u. So that's the chain. Okay, so for x, its derivative is 1. So we kind of have it even if it's e to the x. All right, so let's try these. So if I have e to the 5x plus 2, the derivative, I don't know why I gave so much room, is e to the 5x plus 2 times 5. That's it. So you could write the 5 out front if you want to, but it's pretty simple. So the next one, if I have y equals e to the sine of x, it's going to be itself, e to the sine of x, and then times the derivative of sine, which is cosine. Okay, the next one, f prime of x. Why do I have two b's? C and d, right? I do that all the time. All right, so f prime of x is going to be itself, so e to the square root of x, and then times the derivative of the square root of x. Do you guys know the derivative of square root of x yet? Yeah, it's 1/2 x to the negative 1/2. The way I always write it is 1 over 2 root x. Okay, that's one that you guys should know right away. 1 over 2 root x. So putting it all together, you could have e to the root x all over 2 root x. That would be the derivative. All right, the next one, what do I need to do? Quotient rule, right? So don't forget all the things that you've learned along the way. Quotient rule, product rule, chain rule. All right, so we're going to do low, d high, so the derivative of e to the x is e to the x, minus high, d low, is 1 all over the square of what's below, so 1 plus x squared. Now, every time you use the product rule or the quotient rule with e to the x, you're actually going to have like an e to the x in common. Okay, so if you had like an e to the 2x for both of them, you would have an e to the 2x in common, right? Do you guys see? Because you're always going to have the derivative of itself, which is itself. So on the top here, we have e to the x twice. So every time I do the product rule or quotient rule, I always pull that thing out to the front. So I'm going to have e to the x out front. And then I have 1 plus x minus 1. So 1 plus x minus 1 becomes just x. So I'm going to have x e to the x all over 1 plus x squared. Like that. Easy enough? We like the derivative of e to the x. It's always very, very simple. All right, so how about the next one? Really, I've messed up all my lettering, haven't I? So this is E, F, G, and H. So how about this one? There's a trick. Can you make it easier? Not give up. That's not easy. That's the ultimate easy. All right, what about E and natural log? What if I gave you E to the natural log of 8? You would know right away that it's 8. You guys know that rule? The cancellation property? So what is this? Just cosine of x. So its derivative is negative sine of x. So don't overcomplicate things. You could make it very, very complicated. And you could find e to the natural log of cosine of x times the derivative of natural log of cosine of x, which we haven't learned the derivative of natural log, but it's 1 over something times the chain. So times negative sine of x. And you would see that things would cancel because e to the natural log of cosine of x is cosine of x. So cancel, cancel, and then you'd end up getting negative sine. So it would work. It's just overly complicated, right? Especially when you have to do this cancellation anyway. You might as well do it at the very beginning. All right, so next one. So I have e to the 5x times 5. And I have minus What's the derivative of 4e to the x? 4e to the x itself, right? Anytime there's a constant, you don't have to do the product rule, you just pull it to the front. So 4, and the derivative of e to the x is e to the x. Derivative of sine is cosine. So it's just 5e to the 5x minus 4e to the x plus cosine of x. So you don't have to pull out the e to the x. Well, I guess you can't anyway, because one's e to the 5x, but so that's our answer. All right. One involving a double chain. So we're going to rewrite it as 1 plus 3e to the 2x raised to the 1/2. Okay, so we're going to have y prime equals 1/2, right, because this is in the form u to the 1/2. So when I take the derivative, it's 1/2 u to the negative 1/2. So I'm going to have 1/2 of 1 plus 3e to the 2x raised to the negative 1/2. And then I multiply by the derivative of the inside, right, derivative of u. So the derivative of 1 plus 3e to the 2x, anybody want to make a guess? What do you think? 3e to the 2x times 2, right? So you're going to have 6e to the 2x, like that. So we're going to have, let's see, 1/2 and 6 make 3, e to the 2x on top, all over the square root of 1 plus 3e to the 2x would be the nicest way of writing that one. And this one, woo-wee, this is chain rule to the extreme. So we have sine of e to the cosine of t squared. So right now it's in the form u squared. So when we take the derivative of something that's in the form u squared, it's just 2u. So we have 2 times sine of e to the cosine of t, and then times the derivative of the inside. So the derivative of the inside is going to be cosine of e to the cosine of t times the derivative of e to the cosine of t, which is e to the cosine of t times negative sine of t. There's a lot going on there. Do you guys understand that? So just keep taking the derivative, derivative, derivative. All right. So what if it's not e to the x, but instead like 2 to the x or 3 to the x or something like that? So if I take the derivative of something that's not e to the x, but another number to the x, like if I take the derivative of 7 to the x, the derivative of 7 to the x is going to be itself 7 to the x times natural log of 7. Okay, so you just tack on the natural log of 7. So think about why that's true. If I had e to the x, is it still okay? E to the x times natural log of e. What's the natural log of e? It's 1, so that works. So it still works, okay? The big thing that people do that makes them get these wrong is they will say, like, oh, I have 2 to the x, so its derivative is going to be x, and then I have times 2 to the x minus 1. They use the power rule. Why can I not use the power rule? Like, that is not true. I can't just pull the power to the front and subtract 1. What's different about when we did the power rule? When we did the power rule, our base was always what? Our base was always x. Does that make sense? It's not an x, it's a number this time. That is what's different. Okay, so always recognize that. All right, so for g of x, again, we have to do the chain rule. So we're going to start it out, and it's going to be 2 to the 3x plus 1, so itself, times the natural log of the base, so natural log of 2. But you still need the chain. So what's the chain? Times 3, exactly. So the derivative of 3x plus 1 is just 3. All right, the next one, a little bit tricky. It's in the form 2 to the u. So when we take the derivative, we have, 2 to the u, 2 to the 3x, times natural log of 2. But then what's the derivative of 3 to the x, of the u? 3 to the x times natural log of 3, exactly. Is this making sense? So we're always doing the chain rule at the end. So it's not just in the form like 2 to the x, right? 2 to the x is easy. It's just 2 to the x natural log of 2. So when you have 2 to something else, you do 2 to the something else times the derivative of something else. All right, and then number 3 I'll put down here. So we have y equals 10 times tangent of x, or 10 raised to the tangent of x, a little bit harder. So it's in the form 10 to the u. So if I was taking the derivative of 10 to the u, we know it's going to be 10 to the u times natural log of 10. But we still need the derivative part. We need the derivative of u. So for this one, we're going to do 10 to the tangent of x times natural log of 10 times what? Yep, good job. You guys are good at your derivatives of tangent and of trig functions. Do you know all of them? Yeah, you're going to have derivatives drills very, very soon. You've almost learned all of your derivatives. By the end of this chapter, you will know all derivatives. All right, so number 2 says find the absolute maximum value of the function. So I have f of x equals x e to the negative x. Okay? So whenever it says find the absolute maximum, absolute minimum, or local max, local min, what we always need to do is we need to think about, a curve, and where our curve has horizontal tangents, or sometimes, maybe they're really sharp, like an absolute value or something. So maybe we have a corner or a cusp or something. So we want to know where our slope is undefined or where it's equal to 0. Okay, so what we're going to do here is we're going to take the derivative of f of x, and we're going to set it equal to 0 or set the denominator equal to 0. Okay, this finds what we call critical values. Okay, so we're going to go ahead and take the first derivative. So I have x times the derivative of e to the negative x is going to be e to the negative x times negative 1 plus 1 times e to the negative x. All right, and I'm going to clean it up a little bit. Every time I do the product rule, I have something in common. So I have that e to the negative x I can pull out. So then I have negative x plus 1 left on the inside, which is really 1 minus x over e to the x. So this is our f prime of x. So we want to set equal to 0 or equal to undefined. That's kind of weird to write, but same idea. So we want to either set it equal to 0 or find when it's undefined. Is it ever undefined? Can I ever have a 0 in the denominator? No, like e to the x is never equal to 0, right? So that can't happen. So this part's never 0. What about the numerator? Can you have 0 equals 1 minus x? Sure, at x equals 1. So this is what we call a critical value. So critical values come from setting your first derivative equal to 0 or setting it equal to undefined, right? Finding when it's undefined. So what we do with critical values is we put them on a number line. You're going to do this like 8 million times in calculus. So here's the first one we've done. Okay, we're testing it in f prime. So we did something very similar to this in Algebra 2, and you probably did it in pre-calc as well. Okay, so you would test on the left, the middle, the right, and so on. You guys remember doing that? Yeah. So we're going to test in f prime. Okay, not in the original, in their derivative. So we're going to test numbers on the left and the right. So I'm going to try 0 and x equals 2. So I'm going to find f prime as 0. And I don't actually need to find the number, but I just need to decide if it's positive or negative. Now this one's not hard, it's 1. Right, 1 over e to the 0 is 1 over 1. So that's a positive number. And then if I try f prime of 2, I get 1 minus 2, which is negative on top, and then I have e squared, which is positive. So negative over a positive is a negative number. Okay, so let's think about this, what this means for the graph of f of x. Not the graph of f prime, but f of x, the original. Okay, f prime is the slope. What we're saying is until we get to 1, our slope is positive. So what does that mean? Before we get to 1, our slope is positive. It means that what? It's going up, exactly. So Jamie says it's going up, right? Does that make sense? So we go up. The slope is positive, right? And then once we get to 1, it tapers off to a slope of 0. And then all of a sudden we go down, right? The slope is negative. So that means we're going up and then we're going down. So we do have a maximum and it's occurring at x equals 1. But you have to be very careful because when it says find the absolute maximum value, that is the y value. Right, it's saying how high does this graph go? That's a y value. Okay, so we found the location. We know it's at x equals 1. So now our last step is we go back to the original and we plug in x equals 1 to find the y value that goes with it. Does that make sense? So we're going to find f of 1. So f of 1 is going to be 1 times e to the negative 1, which is 1 over e. So the way we write it is we say max, or I guess I should say absolute max of 1 over e, and we say at x equals 1. So we say what the y value is and where it's located, at what x value. Does that make sense? Okay. I'm going to get rid of the second part of this next question. So it says the motion of a spring is described by f of t equals e to the negative 2t times sine of 3t. Compute the velocity at time t, graph the velocity function, when is the velocity equal to 0? What is the position of the spring when the velocity is 0? Okay, this one's a little bit harder. So they definitely have questions like this. This one was definitely a calculator one. It's not ones that you can easily find without your calculator. All right, so we want to find the velocity function. So when it says the motion of a spring is described, that's your position function. It's saying its position at time t is this. All right, so the velocity function is going to be the first derivative. So the first derivative of f of t equals e to the negative 2t sine of 3t. We're going to do product rule, so e to the negative 2t times the derivative of sine of 3t is going to be cosine of 3t times 3. And we're going to have plus the derivative of e to the negative 2t is e to the negative 2t times negative 2. And then sine of 3t is the same. And we know that we can always pull out the e to the negative 2t. So we have 3 cosine of 3t minus 2 sine of 3t. So all I did is I pulled out that e to the negative 2t. So we want to find when our velocity is equal to 0. So it's kind of tricky. So this first part is e to the negative 2t. Is that ever equal to 0? No, it's not, because it's like 1 over e to the 2t equals 0. That's never equal to 0, so that doesn't work. So the next one is finding when 3 cosine of 3t minus 2 sine of 3t is equal to 0. Okay, that one you could do by hand. It's just kind of messy, so we're going to use our calculator. So what I want you guys to do is I want you to put this in for y1. So everybody do this along with me. Oops. And then I'm going to make sure that it's in radian mode. And I'm going to go to window, well, zoom 6. I'm going to put it in my standard window, negative 10 to 10. Okay, so I get something that looks like that. All right, so we want to find all of the places where the velocity is equal to 0. So there's a lot of points where it's equal to 0. So it'd be like here, 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 here. You can't really see my blue points here, but that's fine. Lots of different places. All right, so on my picture, let me go back over here. It's coming down and then go back up, down, back up, down, back up, and so on. So I want to find that first 0 right there. So I'm going to do second trace 0. Okay, so go ahead and do it along with me. So left bound, hit enter, right bound, hit enter, guess, go to where you think it is. And we get 0.32759, blah, blah, blah. So 0.328, we'll say. Okay, so that number might be important to us. If we think it's important, then we always go back to the main screen. So do second quit, and we store it. So if you hit X, you can actually store values that are from your graph. So if you hit enter, see how it pulls up that number? So you can do store, and we'll store it as alpha A. Okay, so that's stored as A. So if we ever need it, it's there. All right, and then if we want to find the next one, so I go to second trace, 0. Let's say I don't find the one that's on the way up. I find, again, the one that's on the way down with the next one. So like this point right here. You guys see what I'm saying? I'm going to skip that next 0 because I want to see how far it is between them. And we'll discuss why it's that far between them. So I do left bound, right bound, guess. And one would think that it would be like a distance of like 2 pi away. It'd be 1 period away. Okay, but our period isn't actually 2 pi. Okay, so this next 0 is at 2.42 something. 2.422, we'll say. Okay, and I'm going to go ahead and store that value in case I need it. So I'm going to go back to my main screen. So second quit. I'm going to put in x. I'm going to see it's the same thing, 2.421999. Right, I got it. So I'm going to do store, and I'm going to store that as something else. So alpha b. Okay. Let's see how much you really remember your pre-calc stuff. Some of you guys just took summer pre-calc. I have a feeling it's someone from the summer pre-calc that's going to remember this. Okay, just because I'm so good at teaching it. I'll be sad if you don't remember it. All right, so I'm trying to write all of the solutions, every single value for t. So what I can do is I can say, okay, well, t equals 0.328, and I can say plus, but I can't say 2 pi k, because that's not my period. So let's try it. Let's try b minus a and see what we get, and see if it's familiar to us. It probably isn't. But if I do alpha b minus alpha a, I get 2.0943. It doesn't look like pi. It doesn't look like 2 pi. It doesn't look like pi. What is that number? Think of transformations. We don't have sine of x and cosine of x. We have sine of 3x. Close. Not quite pi over 3. 2 pi over 3. You took your period and you divided it by 3. Because remember with normal like algebra 2 problems? Remember when we did parent functions and we did the beautiful math aerobics? Do you guys remember math aerobics? When you guys had a function that looked like 2x squared minus 3, you knew that anything that was inside with the x value did the opposite of what you thought it did. So you knew that it did a horizontal compression by 1/2, even though it said times 2, right? And then we went down 3. Right? The same thing happens with the trig functions. So if I have sine of t, then it starts at 0 and repeats. Oops, that needs to go down further. It repeats every 2 pi. But if I have sine of 3t, that means I need 3 of these to fill that whole space. Right? It needs to repeat the function 3 times in that space. So the period ends up being 2 pi over 3. So it repeats itself starting at 0 and going to 2 pi over 3. Does that make sense? Do you guys understand what I'm saying? So every value is repeated every 2 pi over 3. So we're going to say plus 2 pi over 3k. Okay, and then the last step is we need to find these other ones here, this one and this one. And those are the ones that kind of go with each other. So when we go back to our graph, we do second trace. We find the 0. And now we're finding on its way up, right? So left bound, right bound, guess. So 1.375. So that's going to be the other set of t values. So 1.375 plus 2 pi k, or 2 pi over 3k. Does that make sense? Did you guys get that? And then I crossed off the second question. It says, what is the position when its velocity is equal to 0? Well, you would just go in and you would plug those values in to the original function, the position function, right? So you could easily do that, but we'll skip it. All right, and the last little bit, you could also have implicit differentiation. We'll skip B, we'll do A and C. So implicit differentiation, we just did this the other day. Same thing applies. This should be x e to the y. I forgot to raise my exponent. Are you like, what is that? All right, that should be a exponent. All right, so anyways, I take the derivative. I'm going to do first times the derivative of the second is going to be e to the y dy over dx, plus derivative of the first is 1, and then e to the y. minus derivative of 5x is 5. And then the derivative of 2y is going to be plus 2 dy over dx. So same thing, just like normal implicit differentiation. Did I do something wrong? You make me nervous. Product rule for this first part. All right, so I want to get all of the dy over dx's on one side. So I'm going to have x e to the y plus 2 times dy over dx. And then everything that didn't have a dy over dx on the other side. So I'm going to have 5 minus e to the y. So our answer, dy over dx, is equal to 5 minus e to the y all over x e to the y plus 2. That's it. All right, and then same thing for c. So if I have 5 to the 2y, remember that's in the form 5 to the u, which has a derivative of 5 to the u, natural log of 5. So when you take the derivative of 5 to the 2y, I'm going to have 5 to the 2y times natural log of 5 times 2 times dy over dx. Tricky, right? Because it's a y term. Do you guys understand all of those? The 2 is from the chain. The dy over dx is because it's y. All right, minus e to the x equals 0 plus dy over dx. Okay, so we can get all the dy over dx stuff together. So I'm going to add the e to the x to the other side. I'm going to subtract the dy over dx over, so I'm going to write my dy over dx out front. So I'm going to have 5 to the 2y times natural log of 5 times 2 minus 1, like that. You guys see how I got the minus 1? I subtracted the dy over dx and then factored it out. So your answer is going to be dy over dx equals e to the x over 5 to the 2y times natural log of 5 times 2 minus 1. So like I've told you a million times before, you never know what's going to happen on the multiple choice. You need to know all the different forms that something can be in. So in this very original, like in the very original, that's not what I'm looking for. In the original problem, I have 5 to the 2y. You could actually rewrite that. Like 5 to the 2y, I can think of it as 5 to the 2 raised to the y. See how that's still 5 to the 2y multiplied? Which is 25 to the y. Whoops, not 2 to the 5y. All right, 25 to the y, which has a derivative of 25 to the y times natural log of 25. Do we have that in this problem? Like in our solution, is that kind of there? Yeah, do you guys see the natural log of 5 times 2? Right, if you have 2 times natural log of 5, isn't that just, bring it up as a power, natural log of 5 squared? So that's there, that's natural log of 25. And then this is still 25 to the y. So see all the different forms that they could write it in. That's what's so frustrating about the multiple choice on the AP Calc exam, because they make it hard. They're tricky. All right. So